everyone. This is my video fulfilling my UPE requirements, and I will be talking about graph problems. So, one of the most important algorithms to know in graph problems is the traversal algorithm, and breadth first search and depth first search are one of the simplest one of those. To just to recap very quickly, if uh, if we have a graph like this, a depth first search would go as deep as possible initially, and then it would backtrack and keep going on to visit another vertices. So in a depth first search, we would first visit this, then this, followed by this and that. In contrast to a breadth first search, we would have gone from 1, then 2, 5, 2, 3, 4. But this depth first search algorithm is also equally useful and is very easy to implement using a recursive solution. So let's start with this question in which we were asked if a graph is bipartite or not. And to check if a graph is bipartite, we can try to color it where each vertex is given an arbitrary color and all the neighboring vertices have to be of the opposite color. And we keep on continuing like that. So in this code, I just take one color to be 1 and its opposite color will be 0. And using a depth first search, I start accounting vertices from a node, and then I make sure that if all of its neighboring vertices are unaccounted for yet, which I represent by number 2, I account them with the opposite color. And but if they were already colored and it happens to be that the opposite vertex was of the opposite color, sorry, the neighboring vertex was of the opposite color, we do not go in any one of these conditions. But if it happens that the opposite vertex was of the same color, we return false because in that case the graph is not bipartite. One minor technicality in this problem was that we were not told that we are given a connected bunch. So we traverse through each of these nodes, and whenever we find an unaccounted for vertex, we just start accounting that bunch of connected vertices. And if there was never a case where we collided with the coloring scheme, we return true. But if ever accounting vertex failed, we returned false. And that is pretty much it to solve this bipartite graph problem. Moving on to next one, this is also very similar and will employ a depth first search approach, and it will be one of the simplest. We basically just have to return the level which has the maximum sum, and we can just leave a DFS recursive algorithm to keep going on at each level. It can keep track of which level it is at by one of parameters, and it just stores, it uses an hash map as an accumulator to store the sum, and whichever one is the greatest is returned by the main function. This is also a pretty straightforward problem, and this DFS solution can be made even more optimal by using another non-recursive approach using a stack or a queue. Moving on to this itinerary problem. Here we are given the ends of edges, and we have to construct a path which starts from this initial given vertex and goes on one by one. It goes on like an itinerary, and there are no, and this path is going to cover all of the given graph. And this is also achievable by using a depth first search. We construct the graph and then we just leave our DFS algorithm to start tracing from the initial point. This had a requirement that the solution has to be of the lowest lexical order, which can be taken care by sorting the edge list in ascending order. And yes, this was also a somewhat medium problem as labeled, but one of the most interesting problem was the network delay one. And if you try to think of an initial DFS approach, it is not going to work. So Let me go into this one in a little bit more detail. So what we have to do is that we are given a graph and we have to find in what amount of time will all of these vertex will have received the signal, and these edges denote how much time it is going to take. So what we do here is that we create a partition, and initially on the right side there are all of the vertex. What we do is the first step, we are given that we have to start at this vertex, and at that point we are going to move this vertex from there to the left side of the partition, and in doing that there will be a few edges crossing the partition, and these edges are going to have some weights with 1 and 3, and then in our accumulator, which at the end will account for the minimum time it will take for the signal to have been received at least once by each vertex, this accumulator we just add the smaller of the times. And when we do this, this essentially becomes 0 and this becomes 2. So now 1 second has passed. The signal from here has gone to there but is only midway through this edge. And once this part has received the signal, we can bring that also to the other side of the partition. So now we would have something like this. This edge will now have more things leading off to other graphs, and this one was 2. Now we do this again. We find the lowest weighted edge, bring it to that side of partition, lower all of these numbers and add all of these new edges. And one of the things one of the things useful to achieve that is a priority queue. And yeah, that's it. These were interesting graph problems and can be solved fairly straightforwardly. Thanks for watching this video. Bye.